So let's talk about general potential energy, general systems. So there's actually all kinds of potential energy besides just gravitational and spring potential. Complex star system with multiple planets and asteroids, atomic particles inside molecules, springs or elastic materials that don't follow Hooke's law. Don't worry, for the most part, we're not going to cover these specific examples inside of it. But the idea is that in general, no matter the structure, no matter the origin of it, there is an idea that there is potential energy that can then be converted into kinetic energy. Now, the key thing, a lot of people get confused about the sign conventions for this work is negative change in energy. So let me just explain where this is coming from. Basically, remember when we include potential energy, we're including the Earth in the system. That creates gravitational potential energy, or we include it. Or if we have the spring in the system, we have spring potential energy. So the idea is we have a system, and within that system, there are going to be those internal forces like the spring force or force of gravity, but there are internal forces in here. But those internal forces result in the creation of potential energy, right? That's where our work in change in energy. So overall, we're saying the work is zero, but the energy is consistent of some potential energy plus some kinetic energy. And here's the idea. The energy is constant, which means that the change in the total amount of energy ought to be zero. But the change in energy is going to be made up of any work done by those internal forces plus any change in potential energy. Okay, sorry. The change in energy overall in the system is zero. So what ends up happening is any work done internally is going to there's no external work here. So what we're going to do is anytime we do work, we're going to either lose potential energy or gain kinetic energy, right? The kinetic energy plus the potential energy has to be constant. And so the big idea on this, and I really wouldn't worry about this, I just show the equation just to illustrate, it's just that if the potential energy goes up due to some work being done, then the kinetic energy is going to go down and vice versa because the energy is going to be conserved. This negative sign is really because it's about the internal work, as opposed to when we do work as change in energy, we're always talking about the external forces, external work. Okay, so that's why there's that sign difference in there, and that might throw people off, but that's where that kind of comes from. So let's look at some examples of what this might look like. So given a spring with the following force equations, derive an expression for the potential energy of the system as a function of the spring length x. So if a Hooke's law spring, right, this work that we might do, the integral of f dx, the work here, kx dx, is going to be let me just kind of draw a picture so we get the signs of this correctly in here. If I want to stretch this spring, I do some force to stretch this spring, external force here. Then the spring force itself is going to be trying to pull on it like this way, right? And so if you want to think about the external work would be positive because the spring is going to move out a distance there. So the external work is f dx here, right, which is the integral of kx dx. And if we stretch it a length x, 0 to x, then it's going to be 1/2 kx squared, okay, from 0 to x, which is 1/2 kx squared. Okay, that's how much work we do. Now, if you think about it from the internal force, the spring force itself, the internal force on the work is going to be negative because the spring is moving in the opposite, the direction of the spring force is opposite the direction of the displacement. So the internal force is negative kx dx from 0 to x, and what you get here is negative 1/2 kx squared. Okay, but that's negative the change in potential energy, and so the change in potential energy is 1/2 kx squared. So that's where that negative sign comes in, because the internal force, right, that thing there is creating that potential energy, that change in potential energy, and it's opposite the direction of that external force. So that's why that internal external kind of had that minus sign. That's where that minus sign kind of really comes from in there. What if the spring force is given by this? Okay, then you could either look at the external force due to stretch the spring, but you would integrate px squared dx from, say, 0 to x here. You would get px cubed over 3 from 0 to x, which would be px cubed over 3 minus 0. or px cubed over 3. So here, the potential energy of this spring is px cubed. This is not a Hooke's law. The force is proportional to x squared. That's a different strength of force, but still the same idea here is this work would cause a change. This would be the potential energy stored in that spring. You could do it with the internal force if you wanted to by the same analogy, but you'll still get the same thing here. Okay? So because of this starting point, work internal is the negative change in potential energy, we can actually derive this relationship here. And that is because remember, the internal force of the work is going to be the integral f dx, which is going to be the negative change in potential energy here, right, for this internal force. However, the differential form of this, if you do d dx of both sides, then you get force here is going to be negative d dx of the change in potential energy here, which is just negative du dx. Because the change in potential energy, the rate of change, the slope of the change in potential energy is going to be the same as the slope is just the potential energy itself. Because this is like the initial energy being like a constant value. That derivative would just be 0. Like you could think of it as negative d dx of u final minus u initial. But the u initial being a constant, not a function of position, then like that would go away so that you would just take the derivative of that. But this is the differential form, okay, of that part there. It's just the differential form and integral forms, they're mirror opposites. They're just one is moving the dx up and one is, and integrating, and one is just doing the derivative like this. So this is important to know because that force from that spring or whatever is creating that potential energy follows that. So suppose an object within a system has a potential energy given by this. What is the magnitude and direction of the force at positive x equals 1? So the force is going to be negative du dx. So it's going to be negative derivative of this. Derivative of x squared is 2x. Derivative 4x is 4. So that's going to be negative 2x plus 4, distributing the minus sign. And so at position 1, if I plug in 1, it's going to be negative 2 plus 4, which is 2. Okay, so that's the magnitude of the force. What's the direction? It's positive, so it will be in the positive x direction. Right, because we're doing it x equals 1. Positive x direction, because it's positive force, so it's going to be pointing to the right. If it was negative, it'd be pointing to the left, which is going to be the right in this case. At what location would the net force on the object be 0? So when would the derivative here equal 0? That would be at x equals 2 meters. X equals 2 meters. And remember, when the net force is 0, we would call that the equilibrium position. And we'll talk about more about that in the next lesson, actually.